So now we have to study electrical conductivity of an extrinsic semiconductor. So extrinsic means a doped semiconductor. It can be p-type or n-type. So conductivity, we have to obtain the expression for conductivity. Sigma. Rho is resistivity. 1 by rho is conductivity that we have studied. And here you can see a semiconducting material. Extrinsic semiconductor, doped. Pure semiconductor is doped. So for example, it may be p-type or n-type, like that. A semiconducting extrinsic semiconductor PQ. PQ is an extrinsic semiconductor of length L. And a battery is applied at the ends of the semiconductor. Potential difference is applied with the help of a battery. P is connected to the positive and Q is connected to the negative of the battery. And we know there are free electrons in an extrinsic semiconductor. There are free electrons and holes. So what happens to the electron? Electron will move to which terminal of the battery? Electrons are negatively charged. They will be attracted to the positive terminal of the battery. And holes are positive charges. They will be attracted to the negative terminal of the battery. So like in a semiconductor, we can see both electrons and holes are moving. Both electrons and holes are moving. That is the case of a semiconductor. Who is waiting? Sai Krishna. Then admit here. Okay, so V is the potential difference applied, L is the length of the semiconductor, then E, electric field, is equal to V by L. We have studied that, V by D. That equation we have studied, E equal to V by L. Understand? And the current, total current is sum of hole current and electron current. Both current will add the total to get total current. So let us see what is total current. Yeah, E equal to V by L. Therefore, total current I equal to electron current IE plus hole current IH. Both are in the same direction. Okay. And I equal to NAEVD, that equation we have studied earlier. I equal to NAEVD. IE means NE, number density of electron. VE means drift velocity of electron. So NE, VE, like that you have to give. NE, VE. Then A into E. NAEVD. VD instead of VD we write VE. N in the place of N we write number density of electron, because number density of holes are also there. So we have to write the space that here we have to write what it denote. NE, number density of electron, plus NH, VH. VH is the drift velocity of holes. NH is the number density of holes. So NH, AE, VH. Therefore, I is equal to common factor is taken outside. A into E is common factor into NEV plus NHVH. Then A is taken to the left side to I by A. I by A. What is current per area? Area is the area cross section. Current by area. That is current density. Current density. Okay. Current per unit area is current density. So we know that rho equal to R. So one equation we got, I by A equal to E into NEVE plus NHVH. And resistivity rho equal to RA by L. We know, we have studied that. And equation 1 is V by L, 1 by 3 equal to E by rho. equal to V by L by R by L. V by L and L cancel, we get V by R into A. V by R is I by A. What purpose we are doing all this? We have to show that E by rho equal to I by A, and we should get the expression for rho. We have to obtain the expression for rho. Understand? So first we find I by A, then here also we found E is taken, rho is taken, and E by rho is showed as I by A. So we can equate them. I by A is equal, E by rho is equal to this. This is I by A, this I by A is E by rho. So we can equate this to E by rho equal to E into NEVE plus NHVH. We can equate. We are trying to get the expression for conductivity. So first we take resistivity and then we find 1 by rho is conductivity. 1 by rho, in order to make it 1 by rho is conductivity. So E has to be taken to the right side. So E into NE, VE by E, VH by E, like that it is written, NH VH by E. Why we have written like this? Because drift velocity per unit electric field is mobility. In terms of mobility, we can write the expression drift velocity per unit electric field, that is the mobility. So 1 by rho equal to E into NE, this will be mobility of electron, mu E. Who is waiting, Aaron? Okay. So drift velocity per unit electric field, that is mobility mu E. This is mobility of electron, this is mobility of holes. We can see what is the final expression. 18. Okay, now. So 1 by rho equal to E into NE mu E plus NH mu H. Drift velocity per unit electric field, that is mobility mu E of electron, and VH by E equal to mu H, mobility of holes. Conductivity, there 1 by rho is conductivity, sigma equal to E into NE mu E plus NH mu H. Equation 5 and 6 show that resistivity and conductivity of semiconductor depend upon electron and hole number densities and their mobilities. So conductivity and resistivity, this is resistivity, and conductivity depends upon number density of electrons and holes and the mobility of electrons and holes. Here we can see conductivity is directly proportional to number density, but resistivity is inversely proportional to number density. So for example, if conductivity increases, that happens when number density of electron and hole increases. That happens when temperature increases. So when temperature increases, electrons bonds break, more number of electrons and holes are produced, and number density of electron and hole is increased, and therefore conductivity increases. They are directly proportional. So when temperature increases, conductivity increases, but resistivity decreases. It is inversely proportional. Number density and conductivity are inversely proportional. So when temperature increases, what happens? Gayatri, when temperature increases, what happens to conductivity? Gayatri? Conductivity increases. Okay, correct answer. Okay. What happened to resistivity? Bhadra, what happened to resistivity? Bhadra. Bhadra, are you there? No? Akshay, what happened to resistivity when temperature increases? Akshay. Hello. Akshay. Surya Tej, not Venkata. Surya Tej, Surya Tej. When temperature increases, what happened to resistivity?
Decreases.
Decreases. Correct answer. Okay. So the current density is J equal to I by A equal to E into NEVE plus NHVH. NEVE plus NHVH. Okay. N junction diode that we'll explain with the video. Okay. വീഡിയോ കാണുമ്പോൾ ഇടയ്ക്ക് സംശയം തോന്നുന്നുണ്ടെങ്കിൽ വിളിക്കണം കേട്ടോ. അല്ലല്ലോ.
Two types. P-type semiconductors, in which the doping agents are the...
It's not homeschool. It's really similar, but it's not homeschool. It's online school.
Advertisement.
The trivalent impurities, and in which the majority charge carriers are holes.
P-type semiconductor, we know majority charge carriers are holes. Minority charge carriers are electrons. How is a P-type semiconductor made? Pure semiconductor is doped with trivalent impurity. Pure semiconductor is doped with trivalent impurity. And we get a P-type semiconductor. In that, holes are the majority charge carriers because, for example, indium, aluminum, etc. when added to intrinsic semiconductor, 3 of them make covalent bond with the neighboring germanium or silicon atoms, and for the one of the germanium will not get electron from the dopant atom. So one hole is created there. So one impurity atom create one hole. So as much we add the impurity atom, that much holes will be created in a P-type semiconductor. So in a P-type semiconductor, holes are majority charge carriers. And minority, you see, minority are marked electrons, green color one. That is electron. This holes E plus, E plus, E plus is written. This is electron, E minus. Okay? Okay.
And N-type semiconductors, in which the doping agents are the pentavalent impurities, and in which the majority charge carriers are electrons.
In an N-type semiconductor, how is N-type made? Pure semiconductor is doped with pentavalent impurity like antimony, arsenic, etc., phosphorus, etc. So what happened? 5 electrons are there in the dopant atom. 5 electrons are there in the outermost shell. 4 of them make covalent bond with neighboring germanium atoms. and one electron is excess that can move in the crystal lattice freely, and when one dopant atom is added, one electron is excess in that is free to move in the crystal lattice. So as much dopant atoms are added, that much electrons will get freed and make the material more conducting. So in an N-type semiconductor, electrons are majority charge carriers. That green color one is electron. So you can see more number of electrons, and holes are few. Minority charge carriers are holes. So this is a very important factor about P-type and N-type. P-type, just when you hear it, you must know holes. P means positive. Holes are more, electrons are less. N-type negative. So N means negative. So more number of electrons, less number of holes. Okay.
Consider a p-type semiconductor crystal to which a specific amount of a pentavalent impurity is added in high concentration. This creates a semiconductor crystal that contains both a p region and an n region.
So here PN, next we want to study PN junction diode. That is an important device. In most of the electronic appliances you can see diode. So and its use we have to study. So how is a PN junction? PN, P-type, N-type. PN junction. A junction is formed, and PN junction diode. So here you can see how is it made, a PN junction diode. So actually first we make P-type, and then we make N-type. We cannot just join them. Just by keeping them together, it will not be a PN junction. So either you have to heat it to very high temperature to fuse them, or the easy method, usually that is the practical one. We take a P-type semiconductor, and then one part of it add pentavalent impurity, and then it is heated to very high temperature, so that becomes one end becomes N region and the other end becomes P region. So first you take a P-type semiconductor, and one part of it you have to add what? Pentavalent impurities like phosphorus, that is shown here. P-type semiconductor plus phosphorus, antimony, arsenic, etc. are added, and we get a PN junction. So that will fuse into that, and we get a PN junction diode. Junction is this, P-type, N-type joining part. That is the junction. PN junction is formed. Okay.
The boundary that separates the p region in the semiconductor from the n region is called the PN junction. It is important to note that a PN junction cannot be formed by joining two separate pieces of P-type and N-type semiconductors. Because of the surface irregularities of the two different crystals, and because such continuous contact at an atomic level is not possible. If such a junction is formed, the junction would not be continuous and would therefore inhibit the flow of the charge carriers. Now, let us again look at the semiconductor crystal that contains both the P and N regions separated by the PN junction. We know that in the P region, there is a higher concentration of holes, and in the N region, there is only a smaller concentration of holes. Similarly, in the N region, there is a higher concentration of electrons, and in the P region, there is a smaller concentration of electrons. This causes the holes to diffuse from the P region to the N region across the PN junction. Physically, this means that some of the valence electrons just to the right of the junction may fill the vacancies just to the left to the junction. Simultaneously, the conduction electrons also diffuses from the N region to the P region across the PN junction. The ions do not move because of their heavy masses. This diffusion of the majority charge carriers across the PN junction creates a diffusion current that is directed from the P region towards the N region of the semiconductor.
Okay, here you see. So initially this is P region and this is N region. So when a PN junction is formed, what happened? Here majority charge carriers are holes. Here holes are less initially. So what happened? Higher concentration to lower concentration holes move. Holes move from P to N. At the same time, electrons in the N region, they are the majority charge carriers. They will move to P region. Electrons from N region move to P region. So what happened? Electrons and holes, when they meet, what happened? Recombination take place. Electrons and hole recombination take place. When they cross the junction, recombination of electrons and holes take place. And what happened when recombination takes place? Here, all the electrons are reaching here. You see, that is shown here. All the electrons are reaching here due to diffusion. That is diffusion current. Majority charge carriers cross the junction and reach to the other region. Majority charge carriers. Here majority charge carriers were electrons, they reach here. Here majority charge carriers are holes, they reach here. So near to the junction we can see the electron hole recombination take place. Then it will be ionized. This P region is ionized. This near to the junction, which charge it will get when more holes come and arrange near to the junction? They are actually moving or crossing. So when all the electrons reach here, this end becomes which charge? All the electrons reach here, recombination is taking place, and in effect what will be the charge of this end of the P region? Near to the junction, P region becomes negative or positive? Children, P region near to the junction, P region become negative or positive? Amaldeep, P region becomes what? When they cross each other, when the higher majority charge carriers cross the junction, near to the P region is actually positive, but now more electrons entered into the P region and they are near to the junction. All the electrons are arranged near to the junction. Even though recombination is taking place, in effect it gets a negative charge. And all the electrons come and arrange near to the junction. Effectively it gets a negative charge. P region becomes slightly negative, opposite type. P region becomes slightly negative near to the junction and N region becomes slightly positive. All the holes are coming. So in effect it gets a positive charge near to the junction. It is easy to remember. Opposite type of charge it gets on diffusion current. While diffusing, P becomes N and becomes P, positive. That means slightly positive. So that happens near to the junction. Near to the junction. Here far from the junction it is not like that. Near to the junction, P region becomes slightly negative and N region becomes slightly positive. So what happens is, when all the electrons come and arrange here, further movement of electron, actually diffusion current means electrons cross and reach here. Now due to these charges formed, these are actually charges formed near to the junction. Charge recombination is taking place, but this end the charge it becomes slightly,
When electron
charge it get negative charge only. That means ionized. This part is ionized. That only we can say. They cannot move. The charge is space charge. They cannot move because recombination is taking, electrons come and recombine with the holes. So in effect this end near to the junction, P region becomes negative and region becomes positive. So these charges actually recombination is taking place and then immovable charges are produced. Ions are produced because of this process taking place. Immovable charge carriers are produced near to the junction. Immovable charges, ionized out. Material is ionized due to the motion of charge carriers and they cross the junction, recombination takes place. Due to all these processes, free charge carriers will not be there, but in effect, space charges will be developed near to the junction. N region becomes slightly positive and P region becomes slightly negative. That prevents further diffusion of electrons and holes. This developed due to these charge carriers. Now these electrons cannot reach because this part is ionized, negatively ionized. So these negatively ionized charges will repel all the electrons coming towards it. The negative ions produced here that will repel further electrons moving towards it. Similarly, the positive charges created here, space charges created here, immovable charges created here, that will repel further motion of holes towards it. Further diffusion is opposed because of the charge developed near to the junction. Opposite type of charges are developed near to the junction. They will oppose further motion of the majority charge carriers. So what happens? It behaves as a and this region is known as depletion region. Depletion region, depletion means deplete എന്ന് പറഞ്ഞാൽ എന്താണ്, ഇല്ലാണ്ടാവുക. Depletion region എന്ന് പറഞ്ഞാൽ ഫ്രീ ചാർജ് കാരിയേഴ്സ് ഒന്നും ഇല്ലാണ്ടാവും, അതാണ് പറയുന്നത്. ഡിപ്ലീറ്റഡ് ഓഫ് ഫ്രീ ചാർജ് കാരിയേഴ്സ്. അയോണൈസ്ഡ് ചാർജ് ഉണ്ട്, പക്ഷെ അതുകൊണ്ട് കാര്യമില്ല. ദേ വിൽ നോട്ട് മൂവ്. Ions are heavier, so they will not move. Only electrons or holes can move. So immovable charge ഇവിടെ ഉണ്ടായതുകൊണ്ട് കാര്യമില്ല. They will repel further motion of the majority charge carriers and cross the junction. So what happens? Diffusion current decreases. The region is devoid of free charge carriers near to the junction. The region is, that means N region and P region, both region is devoid of free charge carriers, and there we can see only opposite type of ions developed, and that region is known as depletion region. Depletion means deplete means that vanish. So that means the free charge carriers are not there. Charges are there, they are immovable, but free charge carriers are not there in that region. That's why it is called depletion region. And you know, that opposes the motion of charge carriers crossing the junction. That opposes the diffusion current. So electrons cannot move to this side, holes cannot move to this side. So what happens? Diffusion current decreases. Then when diffusion current decreases, what happens? Drift current develops. What is drift current? So here you see all the electrons, these electrons come and arrange near to the junction. That means recombination taking place, diffusion current, all the electrons reach here and recombination take place, and this end becomes slightly negative and this end becomes slightly positive. So it behaves as if a battery is connected. Potential barrier is developed. Potential barrier is developed. I will show the video. Okay, you listen.
Electrons diffuse from the N region to the P region. They leave behind stationary, positively charged atoms of the donor impurity. Similarly, when holes diffuse from the P region to the N region, they leave behind stationary, negatively charged atoms of the acceptor impurity. This creates a layer of negatively charged ions towards the P side of the PN junction, and a layer of positively charged ions towards the N side of the PN junction. The layer of stationary negative charges towards the P side of the junction opposes the diffusion of electrons from the N side. Similarly, the layer of stationary positive charges towards the N side of the junction opposes the diffusion of holes from the P side. This creates an electric field near the junction, which is directed from the N side to the P side. Thus, a small region is created on either side of the PN junction where no free charge carriers can exist. The region free of moving charge carriers extends on either side of a PN junction and is called the depletion region. The separation of charges in the depletion region creates a potential difference that opposes the diffusion of electrons in the N region and holes in the P region across the PN junction. The electrons and holes have to overcome this potential difference, called the barrier potential, to freely diffuse across the PN junction.
So this is the potential barrier developed. Here, near to the P region, near to the junction becomes negatively charged, and N region becomes slightly positively charged near to the junction due to the immovable ions created near to the junction. Opposite type of immovable charge is developed. Opposite type, P region negative charge, N region positive charge is developed. This acts as a potential barrier. It behaves as if a fictitious battery is connected here. Fictitious battery is connected. It behaves like that. That means here a negative battery, negative of the battery is connected. Here a positive of the battery is connected. It behaves like that. So that opposes the diffusion current. Now electrons cannot reach here because this is negative. Electron cannot cross here because this is positive. So what happened? Diffusion current decreases because of the potential barrier developed near to the junction. And that barrier potential is shown with that violet colored line. Potential difference is developed. Potential difference. And potential difference is developed across the junction. And then what happened? If the potential barrier is overcome by some other means, for example, when we connect a battery, here if we connect the positive, P region is connected to positive and N region is connected to another battery. This is a fictitious battery. This behaves fictitious. Actually, we are not connecting any battery, but it behaves like that. A battery is connected with the negative terminal to the P section and positive terminal to the N section. It behaves like that, which prevent diffusion current. So then how can we overcome this potential? By applying an external potential difference opposite to this barrier potential. We have to apply an external potential opposite to the potential barrier. Then only further diffusion take place. So that case we will discuss later, connecting a battery externally. Now we are discussing about what is depletion region, what is potential barrier, and such things we are discussing here. So here in a PN junction, when a PN junction is formed, majority charge carriers cross the junction, holes from P region cross the junction, and electrons from N region cross the junction. Electron hole recombination take place. And then near to the junction a region is created with the opposite type of charges are developed near to the junction, and it behaves as a potential barrier which opposes further motion, further diffusion of the charge carriers through the junction, and that acts as a barrier. Barrier means what? Barrier is actually opposing. Barrier എപ്പോഴും വെക്കുന്നത് എന്തിനാണ്? ഇവിടം വരെ വന്നാൽ മതി, നിങ്ങൾക്ക് കടക്കാൻ പാടില്ല. Barrier potential, but potential difference is developed near to the junction. And then depletion region, they usually ask that question, what is depletion region? So near to the junction a region is created which is devoid of free charge carriers. Only immovable ions are developed, immovable ions. Opposite type, P region becomes slightly negative, N region becomes slightly positive. And then potential barrier is developed. Okay, and you can hear.
The potential difference across the depletion region gives rise to an electric field directed from the layer of positive charges towards the layer of negative charges. The electric field across the depletion region causes electrons in the P region to move to the N region. This is called the electron drift. Simultaneously, the electric field across the depletion region causes the holes in the N region to move to the P region. This is called the hole drift.
What is drift? Drift എന്ന് പറഞ്ഞാൽ minority carriers cross the junction. അതിനാണ് drift. Majority carriers crossing the junction that produce diffusion current. Drift current എന്താണ്? ഇപ്പം എൻ റീജിയനിൽ മൈനോറിറ്റി കാരിയർ എന്താണ്? ഹോൾസ്. ആ ഹോൾസ് ഇങ്ങോട്ട് പോയി. ഇവിടുത്തെ മൈനോറിറ്റി കാരിയേഴ്സ് എന്തായിരുന്നു? പി റീജിയനിൽ ഇലക്ട്രോൺസ് ആയിരുന്നു. ആ ഇലക്ട്രോൺസ് ഇങ്ങോട്ട് വന്നു. അതാണ് ഡ്രിഫ്റ്റ് കറണ്ട് എന്ന് പറയുന്നത്. മൈനോറിറ്റി ബിക്കോസ് ഓഫ് ദി പൊട്ടൻഷ്യൽ ഡിഫറൻസ്. അതായത് ഇവിടെ ചാർജ് നെഗറ്റീവിലായി, അപ്പം ഇലക്ട്രോൺസിന് എന്തായാലും ഇനി ഇങ്ങോട്ട് വരാൻ പറ്റില്ല. അപ്പം എന്ത് ചെയ്യും? ഇവിടെയുള്ള ഹോൾസ് ഇങ്ങോട്ട് വരും. അതാണ് ഡ്രിഫ്റ്റ്. വളരെ കുറച്ച് ഉണ്ടാവുള്ളൂ. ദാറ്റ് കറണ്ട്, ഡ്രിഫ്റ്റ് കറണ്ട് വിൽ ബി വെരി വെരി സ്മോൾ ഇനീഷ്യലി. പിന്നെ അപ്പം എന്ത് ചെയ്യും? ഇവിടെ മോർ ഹോൾസായി, ഇവിടെ electrons ആയി. അപ്പോൾ when a potential difference is developed, potential barrier is developed near to the junction, the minority carriers cross the junction and that current is known as drift current. Then what happened? Drift current increases, diffusion current decreases, and at last in an equilibrium both becomes equal. Drift current will be equal to diffusion current. Okay.
Drift of minority charge carriers across the p-n junction creates a drift current that is directed from the n region towards the p region of the semiconductor. Thus, we observe that the diffusion current and the drift current across a p-n junction are opposite in direction. We have to remember that at the time of formation of the p-n junction, there is no depletion region. Thus, there is a high diffusion current but no drift current. As the depletion region gets formed, the diffusion current decreases and the drift current increases. In steady state, the diffusion current and drift current become equal in magnitude and there is no transfer of charge at any cross section. Thus, a crystal with p-n junction in an isolated state is electrically neutral.
So p-n
junction with metallic contacts provided at its ends forms a basic semiconductor device called a diode.